Okay, so we start the second session of the day. So the speaker is Chulan Kwon from Myeongji University, Korea, and he will talk about molecular dynamic study of the non-equilibrium motion driven by an external torque.
Thank you. Introduce me.
After 35 minutes.
Okay, yeah. My name is Chulan Kwon. I come from Myeongji University in Korea. I have two collaborators for this work. Donghan Yu is my student, and Yonggyun Jung at KISTI, which is the Korean Institute for Supercomputing Facility. We use molecular dynamic simulation to study the non-equilibrium motion of a colloidal particle in liquid, such as water. And non-equilibrium is driven by external torque. Let's look at a brief movie from the simulation. By applying external torque, the colloidal particles is moving in some moves like some circulation, showing some circulation. So we want to investigate some kind of non-equilibrium properties of the system. And I'll talk about briefly what is the molecular dynamics for non-equilibrium system, and also I show some preparation step for the overdamped limit that mimics the real experiments, and I'll show you some measurements for the non-equilibrium the motion, like autocorrelation function and distribution function work for the work fluctuations and work production rate. And finally, I confirm the fluctuation theorems for the work, and also test the fluctuation theorem for heat. And we'll summarize my talk very briefly. The colloidal particles are moving in the sea of the molecules in liquid, and the molecules are interacting with each other by Ramanujan's potential. So for the equation of motion, this part is denotes the interaction from between among themselves. And I put these two terms. One term is dissipative term, and this part is a random, the random force. And this kind of setup is called Langevin thermostat, where the D and gamma are related. This so-called Einstein relation. And this thermostat helps this reservoir or liquid maintain in equilibrium at temperature T. And the colloidal particles equation of motion is such, and in this case, there are three kinds of the force here. The first part is harmonic, the first, and that's, I think that mimics some confining force in optical tweezer. And next one is a non-conservative force. For this, I choose this non-symmetric matrices, and for different alpha and beta values, this force becomes non-conservative. Actually, this is the non-equilibrium driving force. And the third term, F reservoir, is denotes the interaction of the colloidal particles with the colloidal particles and other molecular particles. And there is the first law of thermodynamics is hold in the system is nothing but energy conservation law. E is the total energy of the system, and W dot and Q dot is the work production rate and heat production rate. Work production rate is work done, the rate of the work done by this non-conservative force. So if there's no non-conservative force, there's no work production. And heat production is nothing but the rate of work done by this reservoir potential. I put this minus sign here. In that way, I define the heat. Heat is the amount of energy transfer from the system to the reservoir. That's just a convention. And equilibrium is possible when there's no non-conservative force. In the case, there's no work production. And as time goes to infinity, the system reaches the equilibrium. In the case, there's no entropy change because the system reaches the steady state, and there's no heat production in the steady state. And also, we expect that the distribution becomes Boltzmann. This is the MD simulation result. Heat production rate goes to a zero value, and simulated result for the distribution and the Boltzmann distribution is agreed with each other. Next, for non-equilibrium is driven by this non-conservative force. In our case, for the case with the different values of alpha and beta. In this case, there is a work production rate. As time goes to infinity, in this case, the system goes to a non-equilibrium steady state. Differently from the equilibrium state, even if there is no energy change, but each of work production and heat production is non-zero. Actually, it is the same in that its average value is the same and always positive. That means in non-equilibrium steady state, there is a continuous production of heat and work. That's the fundamental difference between the Ness and equilibrium state. There are many interesting properties of non-equilibrium. As I told you, the Ness distribution is non-Boltzmann, and incessant production of work and heat, and also the entropy production. And there is a Zarzynski's inequality is found, and this is actually a special type of fluctuation theorem. As a corollary, that this fluctuation theorem gives some irreversibility of the system on also the inequality in the second law. And the entropy production, also Hatano Sasa found there is a contribution, so-called excess entropy. In this case, it is a transient part when there is a time-dependent protocol. And also there's a time-persistent part. This is called housekeeping entropy production. Of course, there's the found that detail balance is broken, and there is a non-zero Ness current in the phase space. And also, interestingly, for a long time, the work and heat production has a large deviation nature, in this case. And also the very interesting thing is heat distribution, the initial memory is always everlasting, et cetera, and et cetera. And this kind of the property can be studied by theory and simulation by using the Langevin equation and master equation. An experiment, a small system like a colloidal particle in a liquid, or optical trap, or some nanoscale electric circuit are studied. But relatively, not many studies are done for this by using the MD simulation. So in this talk, I use the MD simulation and try to find some interesting the properties like these three lines. We prepare the Monte Carlo simulation, not Monte Carlo, the molecular dynamics simulation to be consistent with the overdamped limit. Because we want to mimic the many experiments in overdamped limit. And also we compare the results with the theoretical results from the overdamped Langevin equation. And overdamped limit is given in the case that gamma of C, this is the friction coefficient of colloidal particle divided by the m is much, much larger than this first constant of harmonic potential divided by the gamma C. It is also equivalent condition to where the relaxation time for this fast variable, momentum variable, is much, much less than relaxation time, the slowly varying variable, the position. And this is the R is a radius of a cross section. When R is, we increase R, then the friction coefficient becomes larger. So, and this friction coefficient is expected to satisfy this Stokes relation. So we need to increase the R in terms of this sigma prime, because the sigma prime is actually roughly the position of this minimum of the Lennard-Jones potential is just, it is roughly the size of R. So we need to increase the sigma prime. Also, actually this Lennard-Jones potential is long ranged. So in simulation, we need some kind of cutoff. So when we move this cutoff a little bit, then the interaction gains some more interaction, more attraction. So we expect that the friction coefficient to increase. And actually, we use this cutoff distance as 2.2 times sigma prime. And this is a well-known, optimal value for the water. And how to the estimated friction coefficients? There is the formula for autocorrelation function for position in time. That's obtained from the Langevin equation, is this way. And this is the initial correlation function, which is when the system is prepared in the initial equilibrium the situation, then it's given by this one from the equipartition theorem. So this relation holds for in the absence of the non-conservative force. This is our simulation data. We increased the sigma prime from bottom to top, and we used 1.1 temperature. And this is also the optimal temperature, the value used for the water in the previous MD simulation for water. And we fit this one as from this, and this A is a initial value. So for temperature T 1.1 is expected to be 1.1 is well agreed with this value, and B of C is B is supposed to be the expected gamma of C. So as you see from the table, sigma increases, this gamma C increases, and this is linear. So this linearity confirms the Stokes law in the simulation. Also, this value in this column and this column is large, enough large, much larger than this value. That means we can finally get some overdamped the value of gamma C. Using this gamma C, and for the M is the mass of colloidal particle, is much larger than the mass of liquid molecules is one. So we also use temperature 1.1 and cutoff value of the interaction, the Lagrange-Jones potential is 2.2. And we find autocollision function, in this case for non-zero, non-conservative first. In this case, we can derive this autocollision function from the Landau equation. Here there is the modification factor, which is responsible for this circulating in its nature. So this simulation is also we try to fit this the simulation with this known result, and we found that C0 is 1.0 is close to 1.1. In this case, its gamma C is 28 point something. This is quite close. That means the MD simulation in non-equilibrium situation is well performed. Next one is maybe I'm doing so fast. So there is another important thing is work and heat are produced incessantly in non-equilibrium steady state. In the previous study of ours, me and Jedong and Young-Ki Park, and we were able to derive the work production rate, heat production rate, and as time goes infinity limit, this is value. And using the parameter we use, this one is supposed to be 2.2 divided by gamma C. And when you compare this simulation data, we produced this gamma C very successfully. It's 28 point something. So everything is consistent. Next one is distribution work fluctuation. And P of a small w is a work production rate. And from the simulation, we can get this work production rate from this integral. And simulation, this measured quantity is not constant. That means it's a very fluctuating quantity about the center. And as a result, we were able to find this distribution function for the work fluctuation. This is a broad distribution. And this is the work production rate. The distribution for the work production is produced at during the time equal to 1. Of course, this is a dimensionless time in the system. So our work production, average value of work production is not clear in here, but it's 0.15 something. And this kind of, and for large T, we know that this the work distribution goes to this form. Is in this case f of w. We call this as large deviation function. But this data is not enough to see this large deviation function because time is not big enough. So you can get the we can also obtain this. I believe that we can get this large deviation nature by the further. The examining the deviation, the distribution function at time larger time. The important thing, there is a negative work here region. That means the average value is fine, it is positive, but negative value is always possible. So this is a known fact that the violation of second law is observed by chance, even if the average value is satisfied the second law. Yes?
So this is just overdamped Langevin equations. So it's not the molecular dynamics of the actual big particle in a sea of small particles.
No. Actually, this is a molecular dynamics for the molecular dynamics, but I use larger size of colloidal particles. So it generally naturally reduce the consistent with the Langevin equation in the overdamped.
But the actual simulation is just pure molecular dynamics.
Pure molecular dynamics, yes.
And okay.
Yeah. Next one is the fluctuation theorem. I think the fluctuation theorem is one of the most important discovery in non-equilibrium statistical mechanics. It starts from the Evans and Cohen-Morris's work on this, the molecular dynamics, the simulation for some special deterministic dynamics. Starting from that, there are many. Also, there's many contributions. They show that fluctuation theorem also hold for these stochastic systems. There are many contributors. I cannot put all the names here. So this is the most important names I have. Okay, I have in mind, so I'm not going to show you the derivation of the fluctuation theorem, but I just mention some important thing. Fluctuation theorem is about some time accumulated thermodynamic quantity for during the period tau. So R is equal to this plus this is a Q. So the main part is a common part is Q, and this rho zero is the initial probability density function for the system. But you can choose rho of tau arbitrarily. So that means there are infinitely many fluctuation theorems for the infinitely many possible quantities. But most important quantities, there are three most important quantities here. If I choose this rho of tau as a real PDF, then this R is proportional to total entropy production. Then in the case R, this total entropy production is a change of Shannon entropy and plus heat dissipation at heat production divided by temperature. This part is consistent with the Clausius law. If the initial PDF, if we start from the initial distribution, initial equilibrium distribution, rho zero is equilibrium Boltzmann distribution, and if I choose rho tau as also the Boltzmann at time t, but that may not be the real PDF of the system. I choose just mathematically rho tau as the Boltzmann distribution for a given time-dependent protocol at time t, then this becomes so-called irreversible work, the W minus free energy change between two times. And this case 3 is very seldomly cited. If rho zero and rho tau is uniform, and this first time disappears, so R becomes heat itself. But it is experimentally it's very hard to get this uniform distribution. So it's randomly. It is rarely. It's not possible to realize this case experimentally. Anyways, and there are two kinds of fluctuation theorem. One is integral fluctuation theorem in this way, and this applies to all the cases. The detailed fluctuation theorem only applies to some special case. Among these three cases, only 2 and 3 are applicable to this detailed fluctuation theorem. As a corollary of this fluctuation theorem, this is the result. Corollary result is that the expectation value of R is always greater than 0. So that means the first case is the positivity of entropy change for the total entropy production, or second case is the increase of irreversible work. And in the third case, if you prepare the system in a uniform distribution, then the heat distribution, the production is always always is increased. So they're always finite. That's a generalized second law. And also, there's a special form of the fluctuation theorem. Actually, Jarzynski's famous inequality belongs to this integral fluctuation theorem for work. That's second case. And Crookes fluctuation theorem is this detailed fluctuation theorem. An important thing for this form of fluctuation theorem, you need the initial distribution should be guaranteed. For this W, that is work production case, the initial distribution should be a Boltzmann. So important thing is initial PDF is very important for the fluctuation theorem. So if you do not have a proper initial distribution, then fluctuation theorem does not hold. So in our system, we wait for a long time, sufficiently long time, much longer than the relaxation time for this, and maintaining this alpha and beta is 0. So that means after very long waiting time, the system reaches in equilibrium. At time t0, I turn on the non-equilibrium first, then perform some measurements up to the t equal tau. If tau is a very large value, then the system reaches the non-equilibrium steady state. So in this case, in our specific case, there's no protocol, there's no time-dependent protocol, so free energy change is 0, so we expect the fluctuation theorem for work. This is the simulation data. Here, this function of omega is equal to this form. So this form should be a W when the fluctuation theorem holds. So the data or the data fitting shows that the fluctuation theorem is excellently is shown to hold excellently. And next question is for large T, one can say that Q and W is proportional to T. That means maybe fluctuation theorem for work, as well as the work production, fluctuation theorem for work also hold maybe approximately for a larger time. Is it true or not? Answer is no, because this equality only holds in average sense. But in simulation, in every measurement, the Q and W is not equal, are not the same. This is because delta E, this is a relation of Q and W. The difference is minus of energy change. This energy change, average value of this energy change is always finite. It's not proportional to time. But they can be very large for large initial or final energy. So this kind of inequality is possible for unbound energy system. So this is the result of the function of Q, the same function form of work production, same function of Q and the simulation. And for t equal 1, this is not straight line, so huge deviation in the tail part. If you increase the time near the center region, the fluctuation theorem seems to hold, but in this case, this slope is not equal to 1. So as you increase the time more than this, then this slope is approached to 1. You can find, but this is only not many data because due to not many data, so we cannot show here now, but we can collect more data to show that. So as a conclusion, the fluctuation theorem only holds near the center as time increases, while it deviates very severely in the tail. And this is because this effect, this energy change effect for the unbound energy. And this so-called initial memory effect, we found that this kind of initial memory effect was shown to everlast in the heat distribution for moving potential case, where the trap potential moves with constant velocity case. In this case, there are many works show this fact that fluctuation theorem for the heat is only hold in the center region. So also, our group also contribute this work. So, but this kind of the property is not only for the moving potential case, it's also hold for this another, non-equilibrium case, and another the non-equilibrium driving by some different source of non-equilibrium force. So this is a brief summary. Am I in time, right? 10 minutes. Because everything is clear, I think. It's a summary. So we use the MD simulation to study non-equilibrium motion of colloidal particle. We designed the MD to mimic an experiment in the overdamped limit. But our results, our method does not confine restricted to the overdamped limit. We compare the results with the Langevin equation, and the agreement is excellent. And we confirm the Crookes fluctuation theorem work, but observe that the fluctuation theorem for heat is only hold for near center, the region. Time is left, much time is left, so I introduce my collaborators. Is Hyungyu, and Jaedong is here now. Professor here is still in Korea, and he's kind of a head our groups. You may know, we actually meet every week in chaos. And entropy production is main contributor is Hyunggun, and large deviation heat fluctuation thing is Jaesung and Gwangmo. And this guy, I keep this funny picture because I like it. There's Dr. Jagom is interested in feedback control and information engine, and also a quantum information process. And also, I collaborate with the experimentalist, and we publish some paper in place in the fluctuation theorem for colloidal particle in optical tweezers. And also, we designed to consider another, the work, the combined theory and experiment. This is the special case of special case study, molecular dynamics, and this is Dr. Youngkyun Chung, and this is my student. And also we study some multiplicative noise stuff with Dr. Sabi Drang and Hyung Park. Thank you for your attention.
Okay, so there are a lot of time for questions. Yeah.
When we talk about the detailed fluctuation theorems, what are the restrictions on R? I mean, the time accumulated quantity R, does it have any restrictions?
Yeah, restriction is called involution property. Is how to explain that. But there's a special requirement to satisfy the detailed fluctuation theorem.
So this R, does it always have to be a quantity that we measure in the steady state?
No, it's a finite time quantity. Yes.
So if I introduce an arbitrary time dependence on R, will this fluctuation theorem still hold?
Yes. Yes. In the case, I define work production as the work done by non-conservative force. But if there's a time-dependent protocol, the additional work production is the time-dependent energy, derivative of time-dependent energy with respect to time. That's the additional the work production. Actually, that quantity is the quantity recognized by Jasinski's in his original paper.
What about the role of housekeeping entropy in this detailed fluctuation theorem? If I replace R by the housekeeping entropy?
Oh, actually, by definition, is housekeeping entropy is a little bit hard to measure itself. But as we know that in housekeeping entropy also satisfy the fluctuation theorem. And excessive entropy is always satisfied. So total entropy production is divided into excess entropy and the housekeeping entropy. Both satisfy the fluctuation theorem. But there is some recent work. I don't want to talk about this in detail. For recent work, if the system has odd parity force, like a momentum dependent force. In the case, this composition is not possible. The total entropy production is excess entropy plus housekeeping entropy. But housekeeping entropy, only part of the housekeeping entropy satisfy the fluctuation theorem. So anyway, this is very, mathematical, but we may discuss more.
I want to, it might be very trivial. Can R be a non-thermodynamic quantity?
I don't know. It's mathematically, it's anything, any quantity is true, but only this. This common part is Q. But more generally, if you have some stochastic dynamics, you can have some kind of some disjointed dynamics that might not be the realistic dynamics anyway. Then two path probability ratio, to take the two probability ratio and take the log, that's another the candidate for this R. So there are many possible ways to have the quantity R, but very restricted case is I think that as far as I know, these three cases are the meaningful the quantities in thermodynamics.
Any other questions?
Yeah, to follow up on an earlier question.
Yes.
Were you simulating the Langevin equation?
Yeah.
Or were you doing a real
MD simulation?
Dynamic simulation.
Yeah, real MD simulation. Yes.
So how do you get a non-equilibrium steady state? Why doesn't it just keep heating up forever?
Actually,
you must have some bath or something in there.
If you stir the liquid this way, then you need this kind of force, non-equilibrium force, and you keep this stirring there, then heat is always produced.
But if you're just doing a molecular dynamics,
the
whole system should heat up.
Yeah, there's a heat. Yeah, it's true.
Well, that's a question. It may be language.
Language.
So I think what was meant by the question was, were you simulating the Hamiltonian dynamics of this system, Newton's equation, no friction?
No friction.
That's what you were simulating.
Yes, but we have to include that the interaction between the colloidal particles, the liquid particles, that plays the role of the part in the Langevin dynamics. But it's more confusing. Yes.
The liquid just heats up?
No, not heats up.
Why not? Why does the liquid heat up? What's keeping it cool? You must have a friction or a bath in there somewhere. It doesn't.
Yeah, friction is kind of the effective friction. There's effective friction because of the colloidal particle interacts with the liquid
The
particle.
colloidal particle transfers energy to the liquid
Yes.
via a friction, but the liquid should heat up.
Yeah.
So
No.
you get a steady state.
Even if
I think there's a step we're not understanding.
yeah, provided
State for the particle, this guy is still large enough that like the bath is the remaining fluid acts like a bath for this guy. I guess.
yeah.
How does the work that you measure compare to the total energy of the bath?
What is the sorry?
How does the work that you measure compare to the total energy of the bath?
What is the
work done compared with the total energy of the bath?
total energy of the part? It's very negligible.
Maybe that's the.
Yeah.
You're saying you have lots of liquid
Yeah.
and you ignore the heating up of the liquid.
Yeah, kind of, and also there's some kind of hidden mechanism to keep the temperature of the reservoir.
Oh, there's a thermostat.
Hidden. Yeah, what do you mean? Yeah, go to your equation. You
Okay.
only showed Langevin equations and not actually any Hamiltonian dynamics.
This one. This one is the dynamics for the liquid molecules.
But this is a Langevin equation.
Yeah, but this one is only set up to maintain the reservoir in equilibrium.
But this is what you simulated.
No.
No.
I'm sorry about this confusion. I simulate about this one.
NC.
But what is F reservoir?
F reservoir is this.
It's just
The
that, okay.
interaction between the colloidal particle and
Okay.
reservoir particle. So there's no Langevin equation in simulation.
But do you simulate the liquid molecules? What are they doing?
Both. Actually,
you're saying the
first simulated liquid particles for a long time, and I add these colloidal particles with this additional first.
But the liquid particles are obeying this equation?
Yes, this is.
Okay.
Yeah.
So it's a mixture of
Yes,
molecular dynamics and Langevin.
Yeah, this kind of is a well-known setup for the Langevin thermostat, and there's another thermostat is a Nose-Hoover thermostat. In the case, you put some another kind of a thermostat that keep the kinetic energy of the liquid particles same value, but it's a different setup.
Okay, so maybe I'll just.
Yes.
Okay.
Yeah. Following on this previous question, so you had this detailed fluctuation theorem, right? So, I mean, doesn't have to be. It has to be in the steady state, right? Only then this.
No, it doesn't have to be a steady state.
Because your rho naught and rho r should have the same functional form, so that you can write the forward part and backward part in the same way. So that means that rho r as a function,
Rho tau, yeah.
rho tau as a functional form is not different from rho zero.
No. So we think about the time-dependent protocol, like.
I understand, but what I'm saying, the functional form of rho zero and rho tau
is the same. Yeah,
is the
right.
same. So
Yeah,
that
right.
means it's in the steady state, right? I mean, rho tau doesn't evolve in time.
Yes, right. But rho tau evolves in time.
Tau,
That is not the real PDF, right? That's not the real distribution. Real, I mean, probability density function for at the time t. It's a very tricky, yeah.
No, what I'm saying is that if you write down, for the detailed one, right, the functional form of rho zero and rho tau has to be same, right?
Yeah, okay.
Yeah, so if the functional form of rho zero and rho tau same, that means the system is in the steady state, because if it is in the transient.
No.
So you're saying that rho tau is not the actual distribution of the.
No. For example, there's a time-dependent protocol lambda of t.
Yeah.
Then it's the same function of lambda t. There's rho zero and rho tau is a rho zero function of lambda at 0.
Yeah.
And rho tau is a function of at lambda tau. It's a different function.
And this p is the same on the top and bottom, and the numerator is not like p forward and p reverse. It's the same function p.
T?
P, the probability p function is the same function you are using. It's not the probability distribution for the reverse part and the forward part, right? It's the same probability distribution.
Yeah, forward and reverse.
See, so that's what the confusion is. If it is not for the forwards and the reverse, so there's no subscript. If there's no subscript, then I thought that it has to be in the steady state.
No, not a steady state.
Okay, maybe we can.
Yeah. So the surprising thing for the Jarzynski's identity is that it involves for the time-dependent case, it involves the steady state at two different times. So the final state doesn't have to be a steady state. Yeah. Yeah, right. It's not. It's the same t. Yes. Yeah, same t. Yes.
Yeah, okay, this
Yeah, right.
30 seconds. Maybe I'll just ask one last question. I mean, since you have thermostats, finally the whole system has thermostats, right? The Langevin thermostats. So in that case, wouldn't one can't use the exact proof for whatever fluctuation theorems? I mean, because those are for stochastic systems.
Yeah.
So would those proofs can still be used, right? I mean, like part of the system has thermostats, part of
Right.
them doesn't have. Still, I guess the proofs still work, right? For the work fluctuation theorems.
Yeah. I don't think the rigorous proof for the fluctuation theorem
Right, yeah.
is only given from the Langevin equation.
But finally, this
But
has...
this is a very approximately Langevin. Not Langevin. Okay, the fluctuation theorem holds in experimentally, right? In that case, it's not rigorous.
Okay.
It's not rigorous.
Okay, maybe we continue.
Yeah.
And so let's thank Chulan for nice talk. The next speaker is...